Okay, any questions or issues with the lab? Everyone okay with that? Okay, so today I'm going to continue the lecture from last time. We were talking about transistor level logic or CMOS logic design. Just to briefly review, we started out talking about logic levels, basically voltage levels for representing a 0 and 1, and those voltages have tended to shrink down over the years. Then we talked about noise and noise margins. So the idea there is that logic gates have this thing where they kind of clean up the noise affecting their inputs, because what a logic gate effectively considers a 0 is any voltage between 0 and VIL, right? And then if you look at the output, what's considered a 0 in the output is anything between 0 and VOL, right? So input low and output low, right? The thing is that the voltage input low, though, is generally higher than the voltage output low. So if you have some noise on an input, it will affect the quality of the output, but it'll attenuate that noise, bring it closer to 0. Does that make sense? And then you have the same thing on the other side with the high voltage. So you end up with this noise margin, which is the difference between the output, what's considered low on the output, and what's considered high on the input. That's the noise margin low, right? And then the same thing with the high side, the input high versus output high. Does that make sense? Right. So as long as you have less noise than this noise margin, then things should work. Then we talked about semiconductors, and this is actually a new slide. I put a better slide in than the one I had last time. So silicon, as I mentioned, forms a crystal lattice, and you can dope it. You can add impurities. So you have this, this is the silicon lattice in 2 dimensions. This is what it looks like in 3 dimensions, which is, in reality, it's 3-dimensional. But in 2 dimensions, it looks like this. Every atom forms bonds with 4 neighbors. And then if you put a dopant in, like arsenic, the arsenic is over here in column 5. It has an extra electron, and that electron is free to move around the lattice. And that electron becomes a charge carrier. And the more that you dope the silicon, the more conductive it becomes. It becomes more conductive the more of these dopants you introduce in the lattice. And then if you put an element like boron from group 3 in there, you have this opposite effect where it's kind of a lack of an electron, kind of hole that moves around. So basically what happens is the boron only has 3 valence electrons, so there's a lack of an electron around that boron atom, but then an electron from this silicon atom can sort of borrow its electron for the boron, at which point the silicon atom is missing an electron, right? So that lack of an electron, that hole, has mobility that can move through that lattice, and it can carry current. Makes the semiconductor more conductive. And then if you create a p-n junction where you have a p-type silicon, which is the holes, so p-type silicon is when you have the group 3 dopants, and n-type silicon, which is where you have the group 5 dopants. You put them together, and it creates a diode where if you have a positive voltage of the p side, the anode, relative to the cathode, which is the n side, the charge carriers are attracted to the junction, and then it'll conduct current from anode to cathode. But if you apply the voltage in the opposite way, so if the cathode has a positive voltage relative to the anode, the positive voltage of the cathode repels the holes in the p-type away from the junction. And so this is a reverse bias condition where the the diode won't conduct in the backwards direction from cathode to anode. However, this does still create a capacitor. A reversed bias diode is still a capacitor. So it ends up acting, it doesn't conduct electricity, but it turns into a capacitor, which has implications for transistors. So with the transistor, you have a substrate, which is usually p-type. You put the fusion areas in it, which are little islands. And this is fundamentally how chips are made, is you start out with a substrate, which you grow, and you inject it with these little diffusion areas. These are the active areas, right? So these diffusion areas are basically the way they're made is you start out with p-type. The substrate starts out as all p-type. And then you start doping it with n-type, right? And you can actually reverse the doping by doing that. So in other words, even though this p-type might have had like one of the p-type dopants in it, like, what are they? I always forget. Boron, say. Okay, so you might have had boron in the substrate originally, but then you start hitting it with arsenic. So this thing had boron in it, so it was all p-type, and then I start hitting it with arsenic in these two diffusion areas. You can reverse the doping in those areas and make it n-type. That makes sense? Now you might say, well, what happens to the boron though? I mean, do you end up with boron and arsenic in there? I think so. I don't know exactly how it works, but somehow you can reverse the type of the silicon by adding the opposite thing that had been previously doped with, right? I think what ends up happening is if you have more arsenic in there than boron, then it becomes n-type, right? But it only happens in these islands, and this is where photolithography comes in. You might have heard that term, photolithography. So the way this works is that you apply a mask over the top of this thing, and there's little windows in that mask where those diffusion areas are. So when you hit it with the arsenic gas, that arsenic gas diffuses into the areas that are not covered by the mask, right? So this is all done through a masking process. So basically you protect everything but the n-type diffusion areas, and then you create arsenic vapor, which again, this is why we don't generally make chips in the United States. This is really nasty stuff. Like arsenic is nasty to begin with, but now it's been aerosolized, it's been vaporized, right, into a gas. So now it's poison gas. But you get and it's extremely high temperature poison gas because that's the way you get it to get inside that substrate, right? That's how it gets, you ionize it and you get ion implantation in there through the mask, right? So no one wants to do that work, right? So, but that's basically what happens. And then you end up with this diode, right? Because you've got the substrate, you've got as long as the substrate is grounded, then you get these reverse bias diodes, right? Okay, and then you have the gate, which is in between the two diffusion areas, and then the channel is under the gate, right? So basically, if you want to turn this transistor on, you apply a positive voltage to the gate, right? And that creates a capacitor because in between the gate and the substrate is a little glass, silicon dioxide. So you put a positive voltage here, and that'll create a positive charge. That'll charge the capacitor. That charge will attract electrons, which are not the majority charge carriers in p-type silicon, but they're minority charge carriers. Again, that part I've never, it's weird. Like how's that? We're the minority. The minority carriers are in there. They'll get attracted to the channel, and you end up with a channel. The channel is charge carriers that are forming under the gate. And that will turn this transistor on, and you'll start to conduct from these two terminals, right? So it becomes an electronic switch, right? And this is, of course, what enabled all digital electronics. I mean, prior to this, you had to use a vacuum tube to get this effect, right? Which was like a light bulb, essentially, right? So now the problem here, though, is there is an issue here, though, because I told you before that the substrate was grounded. So you might think, okay, well, here's a capacitor between the grounded substrate and the gate, right? But the problem is that when these charge carriers accumulate in this channel, they become their own thing. They become separated from the substrate. Okay, and that makes it a little tricky to calculate what the voltage difference is between the gate and the channel, because the channel becomes its own thing. It's not part of the, electrically, it's not part of the substrate anymore. Okay? So I'll talk more about that in just a minute. I'll come back to that. So transistors are switches. You can make gates by essentially connecting the switches in series and parallel to create paths that can be on or off with certain combinations of gate values. You guys with me? So if you put two NMOS transistors in series, their gates they have to both be on in order to form a path through that network. You guys with me? It's just two transistors in series, and because they're in series, they both have to be on for the whole network to be on, right? Likewise, if they're in parallel, either one of them could be on, and they'll make a connection. So the idea there is that if you, for example, if you want to make a NAND gate, you can put two PMOSs in parallel between the output and VDD, and two NMOSs in series between the output and ground. And so in order to connect the output to ground, you got to have these guys both on, right? So the input has to be 1, 1 to pull the output down. And of course, if the inputs are 1, 1, both of those PMOSs are turned off, right? Make sense? With any other combination of inputs, though, you'll have at least one of these two guys will be off. And since they're in series, that means you're not going to pull down. And at least one of those PMOSs will be on. Make sense? So it'll pull up to VDD. But they're mutually exclusive. You can only pull up, the output will only be electrically connected to ground or VDD, but never both. Well, I shouldn't say that. It is connected to both during the transient when you're switching. When I'm switching the input from 0 to 1 or 1 to 0, then they are actually both on briefly. You short power and ground during the switching, and that's where most of your power is lost. Make sense? That's called dynamic power consumption. However, when you're not switching, there's very little leakage of current, right? When you're not switching the input in steady state, there's very little current that will go through from VDD, from the power to ground, right? And that's the advantage of CMOS. That's why everyone uses CMOS. It has very little static leakage. Now that's changing because one of the things that's happening is as you lower the voltage, one thing I should mention is that this semiconductor, the threshold voltage that turns on these transistors has been more or less, hasn't changed much over the years. It's usually about 700 millivolts. That's what gets these transistors to turn on. And what's happening is we keep lowering the voltage, right? I think chips nowadays run at 800 millivolts to a volt power supply. And so because we're very close to the threshold voltage, the leakage current is worse in modern chips than it was in previous generation. It's more of a concern. But it's still the most power efficient technology available. Okay, so depending on how you connect the pull up and pull down, you can get different gates, you can get different number of inputs. In general, the number of transistors is 2 times the number of inputs. So if there's 3 inputs on this NOR gate, there's 6 transistors. If I mentioned last time that the CMOS gate, a single gate, has to have at least one bit in the input in order to pull down to ground, right? So because you're using NMOS transistors in the pull down network, you got to turn at least one of them on, right, to pull down. Likewise, in order to have a 1 output, you got to have at least 1 0 input, right? So that disqualifies an AND gate from being created, for instance, because when you have an AND gate, your inputs are 1, 1, and the output is 1, right? But that won't work because if your inputs are 1, 1, there's no way to pull the output up to 1, right? So you can't build an AND gate. Likewise, OR gate works the same way. With an OR gate, if you put all zeros into an OR gate, its output is 0, right? But that's impossible because if I have all zeros, I can't activate any of my NMOS transistors, right? So if you want to create a positive logic gate like an AND or an OR, you have to basically build two gates in series and connect them. You can create a NAND and then an inverter separately, and then you effectively have an AND gate there, but it's 2 gates, it's not 1 gate. Okay, so let's see, I think that's about how far we got last time. So I mentioned that the pull-up network is always PMOSs. The pull-down network is always NMOSs. The reason for that is because notice how the PMOSs are up here next to VDD, right? And that's because what turns on a PMOS isn't actually a 0. We think of it as logic 0. But what it really is a negative voltage on the gate, right? And that negative voltage is because I'm putting a 0 in, but it's being measured relative to VDD. You guys with me on that, right? Make sense? So I need to have a negative voltage on the gate for a PMOS. Why? Because I got to attract the minority charge carriers in a PMOS, which are holes. I got to get holes in the channel, right? So that's the reason why I got to have the PMOSs in the pull-up network, right? And the NMOSs in the pull-down. But if you want to create something like a transmission gate, for instance, a transmission gate doesn't connect to, it doesn't have a power or a ground in it. A transmission gate is when you have 2 transistors in parallel, which allow you to create a tri-state buffer. Basically disconnect, like if you have a wire and you want to be able to disengage it from an output or disconnect it from an output. The problem is that if you're doing that, then this A input is either going to be 0 or 1, right? Well, PMOSs don't pass a 0 very well, and NMOSs don't pass a 1 very well. So the way you get around that is you just use them both in parallel, right? That way you put these both in parallel, and then that way, regardless of what the value of A is, you can pass it over to B efficiently. You guys with me? Okay. Okay, so I mentioned power consumption. I mentioned there's dynamic power consumption, which happens when you switch a gate. Static power consumption is just the power it always uses. And so basically the idea is that the energy to charge a capacitance is the capacitance times the voltage squared. So if you charge up a capacitance, it's C VDD squared, right? That's energy. If you want to convert this to power, you have to measure it through time, right? So if you have the voltage and the capacitance and the frequency, that's frequency at which you're charging, right? Then if you multiply the frequency times that C VDD squared, you get power, right? In watts, right? Except it only costs you when you charge up the capacitors, not when you discharge them. So that's why they put a 1/2 in front of that. So if you have the power, the dynamic power consumption is 1/2 the capacitance times VDD squared times F. Now F, usually people when they put F as the frequency, but it's really the frequency that the transistors are switching. But you know, to simplify this, they usually just put the clock frequency in for that, right? But the clock is not, you don't necessarily have every transistor in the chip switching on every clock cycle, right? Right? Some gates don't switch on the clock, right? Some don't. So, but generally that's just a way, this is just an estimation. Likewise, capacitance, what are we talking about there? Well, you're talking about the total capacitance in a chip, for instance, right? So in other words, you're adding up all the capacitance of all the capacitors in the chip, right? So again, that's just an estimation. But the important thing to note here is that it's VDD squared. The power, the dynamic power consumption is scaling with the voltage squared. So if you're worried about power consumption, you really want to try to get that voltage down as low as possible, right? I mean, you could also try to reduce the frequency, but that doesn't have nearly as much of an impact because that term isn't squared. And then static power consumption is a little harder to quantify. It's basically just the leakage current multiplied by the voltage. And it's harder to measure the leakage current. That depends on the transistors and how much current the transistors are letting through. And that really just depends on the off resistance, right? Because when the transistor is off, it's not really off. It just has a high resistance value. It's R off, right? It's like a 10 mega ohm resistance, right? Does that make sense? So you're going to have some leakage there even through transistors that are turned off, just very little. Of course, the problem is that there's millions of transistors in parallel though. So even though there's a little bit of loss on an individual transistor, there's millions and millions of them that are all losing current, leakage current. Okay, so here's an example question that I might have on the quiz or test. Estimate the power consumption of a wireless handheld computer. VDD is 1.2 volts. The capacitance is 20 nanofarads. That's intended to be the total capacitance. Frequency 1 gigahertz. Again, that's just, the clock frequency is not necessarily, you don't have every transistor switching at the clock frequency, but that's an estimation. And then the leakage current is 20 milliamps. And so you just plug these numbers in and you get 14.4 watts. You have to add the static and the dynamic. So this first term is the dynamic power consumption is 1/2 capacitance voltage squared frequency multiplied together. And then the static is just the leakage current multiplied by the supply voltage, right? So you can get the total power consumption. Okay, so let's come back here to semiconductors. So I mentioned that there's this kind of weird phenomenon that happens when you start charging. You start charging the, well actually normally these transistors, if the gate is, not charged up, it's in a mode called accumulation mode. But as you start charging up the gate, it starts to push the majority carriers out. So in this case, this is an NMOS transistor. I start putting a positive charge on the gate, and those holes in the substrate start moving down away, kind of like a diode, a reverse bias diode. You start to repel the majority charge carriers. That's what happens when you try to send current the wrong way through the diode, is that you have this repulsive effect where the charge carriers move away from the junction. In this case, it's not a junction, it's an actual capacitor separated by glass. But then eventually, you'll attract the minority charge carriers, and they'll form the channel. Okay, so this is called the depletion region, where there's like, you sort of have this effect where you're moving the majority carriers down, and then once the minority carriers start coming up there, you have an inversion region, and then beneath that is the depletion region. Okay, now you might say, well, who cares? What's the point of this? Well, the point is, the reason I bring this up is because this is to emphasize the fact that when you get this depletion region, you have the gate, the oxide, and the channel become a thing, but then this depletion region is going to decouple the substrate away from this channel, right? So the problem here is that when you measure the voltage difference between the gate and the channel, the bottom voltage of this capacitor, you just cannot assume it's ground anymore. The substrate is grounded, but once you get this inversion region, then you have electrically separated the substrate from the channel. This channel is its own thing now. It's its own world. It's not grounded anymore. It's part of it's not at the same voltage as the substrate. Now you might say, well, okay, well then what voltage is it at then? How do you get what is the voltage of the channel is the question, right? Because if I want to know what remember the capacitor is the voltage of the channel of one side of the capacitor relative to the other, right? But now the bottom part of the capacitor is its own thing. How do we figure out what the voltage is? Well, the way you figure it out is it's actually, remember that the diffusion regions are here, and you can get the voltage of the diffusion regions, right? So what ends up happening is that the voltage of the channel is actually just a gradient of voltage between the two diffusion areas. Actually, it's the average of the two. You guys with me? Okay. So why is that important? Okay, well, I'll come back to that question in a minute. So so what do you really want to know when you calculate transistor behavior? You want to know the voltage of the channel, of the gate relative to the voltage of the channel, right? But as I mentioned, figuring out the voltage of the channel is not straightforward. So, to derive that, the voltage of the gate relative to the source, VGS, is the voltage of the gate minus the voltage of the source. The voltage of the gate relative to the drain. And by the way, the source and the drain are just the two diffusion areas, right? Now, they're symmetric. So it doesn't really matter which one's the source and which one's the drain. But there is a convention that the source terminal is the one that's at the lower voltage. Why? I don't know. I don't know why that convention is there. Right? But the problem with that, what kind of sucks about it, is if you have an inverter, right? So here's an inverter, and this is VDD up here, and this is ground, and this is your input, and this is your output. Obviously, this terminal is at the lower voltage, right? Because this one's connected to VDD, right? So this is the source, right? And that's the drain, right? But if you look at the pull-down transistor, this is lower voltage. It's connected to ground, right? So this is the source, and this is the drain, which means that the source and drain are flipped, right? On the PMOS, the drain's at the top. On the NMOS, oh no, they're both at the top, right? Is that right? Drain, source, I guess they are. I thought they were drain, source. No, I guess they are balanced. Yeah, I don't know. I thought they normally switched, but like I said, it doesn't matter. They're symmetric. So let's see, gate source, gate drain, and then the drain source. So try not to get confused here. These two guys have the gate. Gate source, gate drain. This is drain source, which is the voltage of the drain minus the voltage of the source. Okay. So if you substitute in VD, let's see, VDS, VD minus VS, and this is equivalent to voltage gate source minus voltage gate drain, right? Which we don't really care about that. What we really want to know is the gate channel, right? Because the gate channel is the capacitor that turns the transistor on. So the gate channel is the gate source plus the gate drain divided by 2. It's just the average, right? When it's on, not when it's off, right? Let me just emphasize that. When the transistor is off, the gate channel is whatever's on the gate subtracted from whatever the substrate is at. So in a PMOS, PMOS is VDD, on an NMOS it's ground. But once you have the inversion region in here, right, then your gate channel is basically just an average of the gate source, gate drain over 2. And the reason is because you know, you've got the source and drain here, and they're electrically connected to the channel now. So if I want to know what the voltage of the channel is, I just basically take, or it's essentially the average of the two sides. Does it make sense? So, or gate source versus gate drain over 2. Okay, so then they do this, I mean, that's true, but you can also substitute in the VDS, which we get from here, right? VDS is VGS minus VGD, and if you isolate VGD, you substitute in for this VGD, and you end up giving gate channel is gate source minus V drain source over 2, right? So what I'm saying is that this is equivalent to this. It's just written gate channel as a function of gate source and source drain. Make sense? Okay, so what's the point? The point is that we want to know the gate gate channel. Okay, so if, as I mentioned, if we got nothing on the gate, if we don't have any charge on the gate that creates the inversion region, then that's called cutoff mode. If we start to get an inversion region there, we accumulate a charge on the gate, we get an inversion region in the channel, the transistor goes into linear mode, where it just acts like a resistor. They call it linear mode because it becomes essentially a resistor. A resistor in the sense that as I increase the voltage difference between the drain and the source, then I will get a linear increase in the current flowing through, right? However, the problem with that is that as I keep increasing the voltage over that transistor, the drain source voltage, as I keep ramping that up, the problem is that as the voltage here gets bigger and bigger, the gate channel voltage starts to get pinched off near one side. Because remember that the channel voltage is a gradient between the source and drain. If the source and drain are basically the same voltage, then the channel voltage will be the same. But if you start widening the voltage range between the source and drain, then that channel, the gate channel, starts to close the gap between the gate and the channel towards the side that's at the higher voltage. Okay? So it creates this pinch-off effect. And this is called the saturation mode, where you're trying to draw, you have the voltage difference between the source and drain too high, that ends up causing the difference between the gate and one side of the channel to get pinched off. And then the transistor will stop giving you more current as you increase the voltage. So it goes out of linear mode and into saturation mode, and then the transistor becomes a constant current source at that point. You guys with me? Right? So the problem is that transistors are inherently nonlinear because you have to, whenever you're modeling them, you have to consider these 3 operating regions. There's cutoff, where there's basically no connection between source and drain. There's a linear mode, which acts like a resistor until you ask too much of it. You ask it to source too much current, at which point it'll go into the saturation mode and it'll keep giving you whatever the max current was, but it'll peter out. So you can keep increasing the voltage over the transistor, but it won't provide any more current. Okay, so I moved that slide. Hold on a second. Okay, so basically, that behavior will depend on the gate source voltage. Okay? Now you might say, wait, hold on. Why gate source? Why not gate drain? Because remember, this is an NMOS. So here, right? This is an NMOS, right? So we're looking at the gate voltage relative to the source, right? Because the source is at ground, right? So basically, it's gate source. You could look at gate drain too if the source and drain are, if they're at the same voltage. But the problem is that the drain is going to be the thing driving the output of this gate, right? So we want to look at gate source voltage. So the gate, if we have the gate source voltage at 1.2 volts, and then the drain source voltage is increased from 0 to 1.8, you can see that you have this linear effect here until it saturates. It saturates here about 1.6 volts, right? Now, if we have the gate source voltage higher, then the saturation happens around 1.3, 1.4 volts, right? So the saturation point depends on the gate voltage, gate source voltage. Okay, now likewise with a PMOS, it's kind of reversed because the gate source, let's see, now we're at PMOS. Okay, so I did have these switched, sorry. So this is the source and that's the drain. I was right the first time. Right, source is at the top, drain is at the bottom, right? So source, I think the problem is I think that bullet only applies to NMOS, that's why. That bullet point right here. By convention, source terminal is at the lower voltage. That's for NMOS only. I think for a PMOS, yeah, the source is at the top for a PMOS, right? So what happens here is that when you put a 0 into this guy, the gate source, right, here's the gate, that's the source, this is going to end up being negative, right? This is essentially a negative, we're not really putting 0 here, we're putting a negative gate source voltage on, right? So, which makes sense, right? Because this guy has it's a bulk terminal, its body, its substrate has N. This is N type for its substrate is N, right? So we want to attract holes, the minority carriers out of the N. So we got to put a negative voltage here. You guys with me on that? Right? So you're putting a negative voltage on the gate source for the PMOS. And, sorry. Yeah. So we have the negative, like, so for example, the gate source is like negative 1.8. That's like, we're hitting it with the highest magnitude gate source voltage. And then the drain source, likewise, is, again, drain source. So drain versus source, right? Source is at VDD, drain's here. So this is going to be, if you measure the voltage of the drain source is going to be negative here, right? You see that? So if we have a negative 1.8 on drain source and a negative 1.8 on the gate source, it's going to be saturated until you bring that guy down to like negative 1 volt, in which case we go into linear region, right? That makes sense? Okay. So that's called the DC response. Okay, so I want to run through the model. I'm going to go through this kind of quickly. It gets a little overwhelming, but there's just a few points I want to make. So this picture, so this is the picture I showed before. This is a cutaway view, and this is like a three-dimensional view. This is a much more interesting view, in my opinion. I like this one better. So you've got the diffusion areas, and you've got the gate, and you got the bulk substrate, whatever you want to call it. And on this side, I want to point a few things out. There is a capacitor that's formed between the gate and the channel. And there's the VGS, VGD, and VDS between the two. There's also a capacitor between the diffusion area and the substrate. That's not shown here. Over here, you see the same thing. A couple things to call out though. This oxide thickness, this is the glass that's between the gate and the substrate, or the gate and the channel, right? You want this to be as thin as possible. And also the distance to channel is the length. This is how far the current goes from source to drain. Why is that important? Because the current is being carried by charge carriers. Those are the little things inside the lattice, the silicon lattice that move. They don't move that fast. And so you want to make this length short so they don't have far to go, because the shorter the length is, the faster the transistor will turn on, turn off. However, there is this additional dimension that you don't see here, the width. This is the width, and the length and the width are actually the gate length and width, right? Although in general, the diffusion areas are the same length and width usually too. But when you measure the length and width, you're measuring the gate, right? So the wider the transistor is, the more area you have to send those carriers across the channel, okay? Okay, so in the linear region for a transistor, the current that's sent, drain source current, right? And this is obviously, drain source, right? So this is an NMOS because we're dumping current from drain to source. The current's going this way, right? In a PMOS, it would be source drain current, right? It would be switched. So the drain source is the charge, Q is charge, over carrier time it takes the carriers to move, right? The charge is simply capacitance times voltage. And the voltage is the gate channel voltage, which, as I mentioned earlier, it's a little tricky to figure that out, but it's essentially the gate channel has to be calculated relative as a function of the gate and the source drain, right? Or you could do it as, gate source, gate drain, or you can restructure it like this, gate source, source drain, right? Why? Because again, that fourth terminal, which is the bulk, the body of the transistor, the substrate, does not factor into this. The gate channel is only a function of these guys. Okay, so that's what you use for voltage, and then of course the capacitance is whatever the capacitance is. Actually, sorry, scratch that, one thing I forgot. You have to subtract the threshold voltage from that, because the threshold voltage is what's required to get you the inversion region. If you don't, you need the inversion region in order to have that VGC. In order for VGC to be calculated in this way, you have to have the inversion region under the gate, in the channel, and you can't get that until you hit the threshold voltage. The threshold voltage is a property of the semiconductor. Like I mentioned, it's usually around 700 millivolts. That's what's required to get the inversion region, and you start conducting, basically, right? So the capacitor voltage, you have to subtract the threshold voltage. And so the charge of the channel could be calculated like that. I'm just substituting these in. And then the capacitance of the gate is the dielectric constant of the oxide material, which is silicon dioxide. It's glass. It's a really good, I think it's the best insulator, right? It's a really good insulator. Maybe not as good as a vacuum, but it's a great insulator. And then you multiply that by the area of the capacitor, which is, the area, width times length, and then that's divided by the thickness of the oxide, how close you get the two plates of the capacitor together, right? And then, so yeah, that's, 3.9 times the what's the letter? Epsilon, thank you. Epsilon 0, that's the dielectric constant of a vacuum, epsilon 0. Okay, so so basically you could substitute in just capacitance of oxide for epsilon oxide over thickness of oxide, because those are things you can't change. Those are Those are baked into the fabrication technology. But you can change the width and the length of the transistor gate, right? So this C oxide becomes a technology parameter. That's who you get that from TSMC or whoever's making your chips. Okay, so then you can build this in you get charge of your channel is C oxide times width and length, which is the capacitance of the channel, and we multiply that by the voltage. And then we need the carrier time. The carrier time is a function of the carrier velocity. The carrier velocity is a function of this mu, which is the mobility of the carriers. Again, that's just how fast the carriers move in the silicon, times the electric field strength, E. And the electric field is just the voltage of the drain source voltage divided by the length of the channel, right? And so we can then calculate the carrier time. Let's see, carrier time, blah, blah, blah. So we come back up here. So we have the mobility multiplied by the electric field. The electric field is here and multiplied by mu. Right, so we just get this. And then the carrier time then becomes L squared. So we have the V. Wait a minute, I got lost here. Carrier time is mu times E. E is VDS over L. E is the yeah, so this is V, this gives us V, so we have just mu times VDS over L. And then the carrier time is in the denominator there, right? You see the carrier time's in the denominator. So we flip, so this is in carrier time, though. This should be current, right? It's relative, the current is going to be relative to L squared, because we also have L in the numerator as part of the charge for the channel, the channel charge, right? So we have L there, and then we have L here in the denominator, but then that's part of the carrier time calculation. So right, so so IDS is going to be, for the linear region, so what you end up doing is you have this beta term, which is the mobility times the thickness, the oxide capacitance over width and length. That beta term is going to be your technology term, because the mobility and the carrier, the oxide capacitance is baked in. And the width and the length, you're typically you can control those as a designer, but you're going to typically use your minimal values when you're doing digital logic. So the length is going to be, like when you hear about Intel has their new 4 nanometer technology, right? That's the length, right? It's whatever the minimum feature size is, which is the minimum feature size you want to use is the length. And the width is usually like 5 times the length at a minimum, right? So those terms can be baked into beta, and then the beta is just then multiplied by the voltage of the voltage of the gate relative to the channel. So that would give you the linear region. The cutoff region is 0, and then the saturation region, which is where the drain source is greater than the saturation voltage, is this is where it turns into the transistor turns into a constant current source, which is going to be beta over 2 VGS minus VT. Notice that the difference here is that VDS is not part of this, because VDS, once you saturate, the current is no longer a function of VDS. And also the mobility, the one term in here that differs between the NMOS and or PFET and NFET is the mobility, that mu term. So holes, which you have in the remember that the holes are the minority carriers in the if you have the NMOS, NMOS is going to have diffusion that's going to be N, and the bulk term is going to be P, right? And so the carrier over here with the NMOS is going to be the electrons, right? Because the substrate is P. Over here with the PMOS, the substrate is N, and the minority are holes there, right? So holes have less mobility than electrons, which means that the mobility of a PMOS transistor is about half of that of the NMOS transistor. So what you end up having to do in order to balance those out is the PMOS has to have, the way that you compensate is you have twice the width, right? So basically, the mobility term in this beta, you see the mobility here? That mobility is half for PMOS. So in order to make up for that, because that is half, you have to double the width, right? So the PMOS transistors have double the width, same length, but double the width. So if you look at a layout, you'll see that the PMOSs are usually taller, twice as tall as the NMOSs if you're looking down on the mask, on the design. Okay? Oh, shoot, I'm out of time. Okay, any questions about that? Okay, so I think we've got two lectures left. My plan is that in the next lecture, I'll finish talking about the CMOS stuff. The last topic I want to cover is delay and how you calculate delay using the RC delay model. I talked a little bit about that already, but basically, if you build a circuit with transistors, you can calculate the resistance and the capacitance and then use that to figure out the delay. And so this is where we get the propagation delay that I talked about in the delay lecture. And then in the last lecture, I'm planning just to do a review for the exam. Is that okay with everyone? Okay, so we'll just have one more new content lecture next Monday, and then the week after that, we'll do a review for the exam. Okay? Any questions? Okay, sounds good. Thank you. Have a great Thanksgiving.